Okay, physics. So let's talk about uniform circular motion. So this is going to be a special case of circular motion and our first introduction to things that are going in circles. A couple of important points to this. So we do this when we're doing forces because, yeah, so this is an example of a force that's being applied, but it's not changing the speed of an object. It's actually to change the direction of the object. So let's think about this. So here we go. Let's have this, this dude who's spinning something over his head. So this is designed to show you that this line going through this person's hand, this is a hollow tube, and it's supported just by the weight of some washers here. So what's happening is this bob, we'll call it, on the end of this line is going around in a circle. So notice the speed that it's going at is constant. So this is what we're going to call uniform circular motion. So it's moving at a constant speed, but it does not have constant velocity, right? So velocity includes direction, but notice the direction of this is constantly changing. So there's a force being applied, but that force is acting to change direction, not the speed. And obviously from this one, the force is a tension, and that tension is coming from gravity acting on these washers that are at the base here. So let me diagram this out for a little bit so we can think a little bit about it. So a couple of really important things to go on here. So let me switch to this, right? So we're going to talk about uniform circular motion, and there's going to be a force that's applied. So here's my bob, in that case, that was going around. If it was on the left-hand side, there is this force of tension that was acting in one direction. So we'll get into the vertical forces in a second video. They are important, but I'm going to ignore them for right now and assume they cancel, which they don't, but it's close enough. So I have one force acting this. So what's happening, right, as this goes around in a circle, we look on the top view, right, and that tension is acting to change the direction. So what's the velocity? Well, the velocity is always going to be going at a tangent to this. Right? And if I cut this string, that thing would proceed straight along a path, right? So to change direction, I need to apply a force. If there's no outside force, something's going to go straight. So, so we have a few special phrases that we're going to use for this, right? So, so overall, there's something that's causing it to go in a circle, and I'm going to call that my centripetal force. Centripetal. So this is center seeking, right? Center seeking. So it's my force is always going towards the center of the circle to make it. This is going to be the sum of all the forces acting in the direction of motion. Right? So I'm going to be careful about this. So if I was to draw a force diagram, I would never put on a force diagram a net force, right? It doesn't make sense, right? So okay, like here's gravity, here's there's a normal force, and here's my net force, right? It doesn't make sense, right? It's a composite. It's a compilation of them all. The same is true for centripetal force. So write this down someplace. Centripetal force never shows up on a force diagram, right? It must come from something, right? So in this case, my centripetal force is coming from the tension that's being applied here. And there are going to be different things that can provide this. So when we get to planets, we'll look at how gravity can provide that force. In my next video, I'll talk about the gravitron and how a normal force can provide that centripetal force as well. But something physical has to be providing that, and the centripetal force is not a physical force. And I can write this also in terms of Newton's second law, right? So I can say acceleration, my centripetal acceleration, is going to be my centripetal force divided by the mass of that object. So what do we mean by centripetal acceleration? Well, it's kind of funky to think about, but I have this force that's acting towards the middle, right? And mass doesn't have any direction, so there must be some sort of acceleration that is experienced. In this case, the acceleration is not acting to change the speed, is acting to change the direction of velocity. So a subtle point here, because acceleration is a vector and force is a vector, these two will always be pointing in the same direction. So my acceleration vector is going to be pointing towards the center. Center seeking as well, my centripetal acceleration. Okay, a couple of key things here. So notice I put my velocity here. So we'll refer to this as tangential velocity. We'll call this a t. So this is going to be tangential. So if I take an instant in time, and look at the velocity that exists at that point, my velocity is going to be acting as a tangent to the circular path it's going in, and we'll call it tangential velocity. So I can calculate the speed of this, right? So here's what I'm going to think about. So I'm going to figure out, well, what's the time it takes to come all the way around? So time for one cycle, and I'm going to call this the period, and I'm going to make this a capital T. So we're going to have multiple uses for capital T, right? I've already used it for tension here. Sorry, we're just out of letters, right? But capital T can also mean period, which is the amount of time it takes to go all the way around in a circle. So how far have you traveled in one circle? Well, geometry, right? So my circumference is going to be 2 pi times the radius. I'll use capital R just for simplicity. So I can figure out my tangential velocity a couple of ways, right? So if I know the period and the radius, well, it's going to be my total distance traveled divided by the time it took me to get there. Right? So I can figure out my tangential velocity, or my instantaneous speed will be 2 pi r over the period. So this is one handy way that we have to get to velocity. This is not an equation that's given to you. You can kind of suss it out from some of the formulas we'll get to later, but this is not one that's given to you. It's really helpful to remember that you can do this, right? So distance over time is going to give you speed. Second really handy formula is that we have a shortcut for centripetal acceleration, which is going to be my tangential velocity squared divided by the radius of that. So notice I have two equations that I'll use for this, and a lot of times we smash these together. Right? So I have an equation for Newton's second law, which says my net force acting to make this go in a circle, so my centripetal force divided by the mass is equal to my centripetal acceleration, and also I know my square my tangential velocity divided by the radius. So two things that we'll use. So these 3 bits of math should help you as you're looking at the questions. I'm going to go into a couple of more complex examples. So we'll get into things called conical pendulums, the gravitron, and another example that's a little bit tricky to think your way through. So let me toss that at you in a second video. Hope that helps. Talk to you soon. Bye.